Hi class, this is Ms. Jacoy. So this is going over page 28 in the energy packet. So as always, when you're solving a problem, make sure you read it carefully first, and always look at your diagram if they give you one. So we have a small block of mass m is released from rest at the top of a curved frictionless ramp as shown above. The block slides down the ramp and is moving with a speed of 3.5 v naught when it collides with the larger block of mass 1.5 m at rest at the bottom of the incline. The larger block moves to the right at a speed of 2 v naught immediately after the collision. Express your answers to the following questions in terms of the given quantities and fundamental constants. So remember, when they tell you fundamental constants, they're most likely just talking about G. So the first question they ask is determine the height of h of the ramp from which the small block is released. So remember, the easiest way, or the way you should always think about solving these, is one, energy, and this is your energy packet, so it's energy. And then anytime it mentions collisions, you should be thinking momentum. So if you have not yet solved this, go back, solve it on your own, come back for the answer. Please grade your answers in pen so I can tell where you did your own work and where you needed to get help. Pause the video and do that now. Okay, so now that you've done it on your own, the easiest way to determine the height of this ramp is using conservation of energy. We know at the top it has potential energy, and when it gets to the bottom it should only have kinetic energy. So we can say at the top it has some potential energy, mgh, and then at the bottom it has some kinetic energy, 1/2 mv squared. And then you can fill out any constants. G is a constant, H is a constant. I already did the capital M, it's just capital M. The only one we should change is they said it has a starting velocity of 3.5, or had a velocity at the bottom of 3.5 v naught. Remember, when you do that, you are squaring the whole thing, not just the part of it. So then from here, remember, anytime you have something on both sides, if you divide it, it's just going to simplify to 1, so we don't need to worry about it. And then we are solving for h, so you just need to move g over to the other side by dividing. And if you want, you can leave your answer just like this because it's using the constants, or you could simplify it. That's just a little bit of extra algebra I don't feel like doing. If you did, that's great. As long as you got here, you can do the rest. So that is our answer for the height. Moving on to part B, and that is determine the speed of the small block after the collision. So anytime they mention collisions, you should be thinking conservation of momentum. So we have the momentum of our small block in the beginning, or just our m block, and then later we have both the momentum of our little m block and then the momentum of our much bigger 1.5 m block. And so once you understand where your momentum is in the both beginning and after, you can then plug in your equations for them. So we have some mv for our little one, and then some mv later, and then our 1.5 mv, and then fill in your values. So your m's don't change, and then we have 1.5 m. So our velocity, when I say beginning, I say right before the crash, which is the 3.5 v naught, and that should be equal to whatever our velocity is after, and this is your unknown because you want to figure out what is the speed of the small block after the collision. And then we have our 1.5 m, and it says it was moving at a speed 2 v naught. So again, one thing you can notice that there is a capital M in every single one of these parts, so you can again simplify out. Remember, it has to be in every part of it, so that means if I divide each one by m, it should all simplify to 1. Alright, so now that we have that, I'm going to rewrite it off to the side in different colors so it's easier to see. 3.5 v naught should be equal to whatever our v is plus 1.5 times 2 v naught. So hopefully you know 1.5 times 2 is just 3. So we have 3 v naught plus v equals 3.5 v naught. And lastly, to solve, move everything to the other side. So we're going to get 0.5 v naught is equal to our v for our smaller block. Alright, and then part C asks, the larger block slides a distance d before coming to a rest. Determine the value of the coefficient of kinetic friction mu between the larger block and the surface in which it slides. So remember, whenever they are starting to talk about mu, we're definitely talking about friction. And if we're talking about friction, we're talking about a force. So remember, the force of friction is equal to mu Fn, but we are not allowed to use Fn because it's not part of the given quantities or fundamental constants. But by the time it is here sliding, it is just a flat block on a surface that is neither going up or down. So your Fn will be equal and opposite to your mg. So you can just plug in mu mg for your friction. And then if they're mentioning a force in the energy problem, they are without a doubt referencing work. And in this case, since it is moving to the right, but the friction will point to the left, you're going to do negative work because you're going to be losing that energy to heat. So remember, work is force times any parallel distance. If it's anti-parallel, or if it's opposite of the direction of motion, it will be negative. And then you can just plug that straight in there. So your friction equation for your force, and that should be equal to any work done. And then we know that the block comes to a rest. So in the beginning, it has some kinetic energy, and all that kinetic energy is lost because we did negative work or there was heat. So we know that we had kinetic energy, we did work, and we ended up with no energy left in our system. So at its base, that means any kinetic energy we had all gets transferred to that work or due to that force from friction. With that in mind, you should set up your equation of 1/2. That's a 1.5 m because that's our larger block. And then it's going 2 v naught squared. So don't forget to also square that 2. And then it's equal to mu mg times some distance d. And I didn't, but you should always capitalize it because that's the way they gave it to you. Alright, so now that you have this full equation, the only thing left to do is just some algebra so that you solve for mu. I tend to like to simplify before, but it's not necessarily important. You could simplify after. So you're going to get 4 v naught squared, 1.5 m, and that's half of that. Better yet, do half of 4 because that's really easy to do in your head. And then we have mu, and remember that should be 1.5 m here, and then g times the distance. So you'll notice you could either cancel out your m's or you can actually cancel out 1.5 m because they're the same in both places. Always try to simplify, make your life easier. And then 4 divided by 2, 2 v naught squared equals mu g times distance, and then divide by g and d on both sides to get 2 v naught squared over gravity and the distance. Alright, and then on to the last problem. So again, this is talking about the collision. So we should think back, okay, we had a collision, we have our velocity from both, for both of our objects. Now we want to think, is it elastic or inelastic? So you have to know the definition of these. Remember, momentum is conserved in both cases, but energy is not. Energy is only conserved in elastic collisions, but not in inelastic. So they're essentially asking, was my kinetic energy in the beginning of my single block equal to my kinetic energy of both blocks at the end? And the easiest way to solve this is just plug it in. We have our velocities, so we know that in the beginning we had 1/2 m 3.5 v naught squared for our first block, and then at the end we had that same little mass, and it was only going 0.5 v naught squared, and then we had our larger mass of 1.5 m going 2 v naught. So again, I'm going to just simplify this. Notice you again have an m in every term. You can cancel and should. And then you can square everything. You also notice you have a half in every term, so you should cancel that as well. So we just end up with 3.5 v naught squared equals 0.5 squared v naught squared plus 1.5, do 4 because I can do that in my head, squared. And so your goal is to figure out, is this true? Are they equal? So will this side equal 3.5 squared? So this is where I would use your calculators, because I can't do this in my head. If you can, you know, power to you, good for you. But 3.5 squared is 6.25 v naught squared. This is going to be 0.25 v naught squared. And then this is going to be, alright, quick correction. That, as you may have noticed, is not it. I plugged that in my calculator wrong, which is why I hate numbers. But that's going to be 12.25. And then this, when we plug it in, is just going to be 6 v naught squared. So you can add it now if you want, but that's just going to be 6.25, which is definitely not going to be 12.25. That means it is inelastic. So remember, if it asks you to justify your answer, you should and can include work, but you should also include words. So you need to explain the idea that since our kinetic energy at the beginning is not equal to the kinetic energy at the end, we lost energy, so it is an inelastic collision. You also could have probably gone on with the idea that since if both blocks move forward and momentum is conserved, that means they're both going to have to slow down if their velocities are in the same direction. The only way for momentum to be conserved is or for kinetic energy to be conserved and it to be elastic, it has to bounce off, which means the tiny block needs to be going the other direction, which didn't happen in this case. So by default, it's not going to be elastic just based on knowing that fact. Alright, hopefully this video was helpful, and I will see you guys later. Bye.